And welcome to another episode of No, this is not Containers from the Couch. We haven't done a takeover of the serverless office hours, but we are filling in for the regular hosts. And you might have seen us a couple of times before on streaming on Twitch. And if you haven't, I think we can kind of introduce ourselves. So, Olly, can you please introduce yourself, who you are, what you do, and what is your favorite fish and chips flavor?
Sure. I'm not sure what that means, but yeah, sure. So, hey everybody, my name is Olly Pomeroy. I'm a developer advocate here at AWS, and I'm part of our container services team. So specifically, I work on Amazon Elastic Container Service, or ECS, and AWS Fargate. They sit under the serverless umbrella here in AWS, so they're what we call like our serverless containers offerings. And I help customers adopt those services and help work on content for those services. Um, Favorite fish and chips flavor is an odd one. I think that's a reference to the fact that I'm based in London and British. I guess like the traditional thing is you have battered cod with your fish and chips. So maybe type of fish and cod works, but I apologize if that offends somebody.
I put you on the spot. That's fine. My name is Maish Saidel-Keesing. I'm also developer advocate here with AWS. I worked a good number of months or years with Olly on the same team. I'm now a developer advocate for Israel working with the Israeli customers in the market. And I'm not going to ask myself what my favorite fish and chips flavor is, but I'll say one of my favorite Israeli food probably is falafel. So that is something
Nice.
you can learn about us from over here. But today we are kind of going to be talking less about serverless, but kind of about serverless. So, Olly, can you kind of give us what we're going to be? What is the topic we're going to be speaking about today?
Yeah, absolutely. So today we're going to dive really into some of the features of AWS Fargate. And AWS Fargate, we kind of call our serverless containers data plane. And one of the common questions we get, maybe similar to the serverless and the Lambda side, is how can we start containers quicker? Um, Traditionally, when people start up containers on AWS Fargate, there's a little bit of a delay where we download container images and get everything ready. And we're constantly working behind the scenes to like reduce that delay and make it as almost seamless as possible from when you want a container to having a container running. And so today we're gonna dive in to AWS Fargate. We're going to talk about how it works and how it starts your containers, and then we'll talk about ways that we can then optimize that to make it start containers a lot quicker.
Okay. And if you're wondering why we're here on the serverless office hours with containers, so Fargate itself is a serverless compute platform. In other words, in a way, it's very similar to the fact when you're using a Lambda function, you don't have to worry about the compute underneath. You just write your code and you provide the entry points and the handler and the connection to your event or where your trigger comes from. With Fargate, it's kind of, in a way, we do the same kind of thing, but we do run a container. But as AWS, we take care of the compute underneath for you. In other words, there is a small micro instance which is launched directly for you in order to host your specific container, and it's highly contained, and it's all managed as a part of the service, so you don't have to worry about that. So that's what is kind of connected with serverless today.
Yep, absolutely.
So that's the wrong slide. Fine, there we go. Perfect. So Olly, if we're talking about faster, firstly, why do we want faster container image loading? In other words, where do our customers see this as a problem? And specifically with Fargate, why is it a problem?
Yeah, absolutely. Yeah. So there's kind of like two. Well, there's actually probably quite a lot of use cases, but there's two that I want to talk a little bit about, and we hear maybe the most often. And so when people think of applications that are suitable for containers and applications that are good for candidates for ECS, is they think of like web applications. And one of the beauties of using containers for web applications is that you can horizontally scale. You can start new web servers as traffic increases, and then you can scale them down as traffic decreases. But on that scale up, when you're frantically trying to meet the user demand as things are scaling, you want that scale up to be as quick as possible. And so that's one of the areas where we as ECS and Fargate, we get asked, like, what is the quickest way that we can reactively scale up to meet demand. And then on another use case, and this is a second use case I'm hearing quite a lot more actually these days, is when related a little bit to the serverless world, is people start to use containers for event-driven flows. And when events happen, like messages and message queues or event triggers happen, people start a container, do some logic, process some data, convert some images, whatever it may be, and then that container disappears again. The container spins up, processes the event, and disappears. And if it's part of a synchronous flow, you know what I mean? So there's there's follow-on actions from that container. The time it takes for that container to get up and running and do that piece of work is also an area where we want to optimize, and we want to be as efficient as possible.
And for the customers which are probably maybe not that familiar with containers, I'm trying to parallel this slightly with Lambda. When we're talking about Lambda, you provide the code, okay?
Yes.
Or the customer, whoever the person in the account provides the code. But you pretty much don't have any input, or I wouldn't say not input, but not more control of what the underlying operating system which is running at the bottom. So we can kind of say that the underlying operating system is pretty much the same for all Lambda functions, but we just inject your code specifically for that specific use case. When we're talking about container images, firstly, they're usually a lot larger than however many lines of code you have in Lambda. It's a couple of megabytes to, depending on how well you build your container image, to a couple of gigabytes of information. So that takes time to pull that information down into and start to launch that actual instance, or the task, what we call a task inside Fargate. And secondly, it's differs from customer. In other words, it's not one standardized operating system where every single customer runs their same containers on as the container runtime. The container runtime will be the same, but the actual operating system in the container itself is not the same for every single customer. So it will differ. So there's no way to kind of provide the same, what the word I'm looking for, experience and launch times for every single container coming up onto your into your account and within your tasks.
Absolutely. And it's that level of variety, and that we're not quite sure what container we're going to be launching next and what it's going to be built on, or it makes it a really hard problem to solve. Like one moment we could be launching a machine learning framework on a Ubuntu operating system in a container, and then the next we're launching a .NET framework container on Windows Server. Right? There's such a variety of stuff people put into containers, and it makes it hard when we want to optimize container images and make container images and container image data so close to the compute. It makes it a real trade-off of like, what data can we put close to the compute that is more than likely going to be used a lot. If that makes sense. And I think
Yes.
one of the reasons, I'm sorry, I'm just changing my screen a little bit behind the scenes, is this is more prevalent, I suppose, on the Fargate side. And I'm just going to share a diagram, hopefully. Wow. Okay. And this diagram actually talks a little bit about the AWS Fargate architecture and a little bit about why this may be a problem. So traditionally, people have run containers on EC2 machines. And on EC2 machines, you can run lots of identical containers on the same box, and you can put loads of containers on there and really drive up the utilization. And what that means is to download your container image and to download the data, you only have to do it for the very first container on the EC2 instance. And then for all of like the parallel container launches, there's no data that has to be moved around. You can start the container almost instantly. That architecture changes slightly when you move to AWS Fargate and when you use Fargate, and that's because we have a strict isolation model whereby we will only run a single workload on each underlying piece of compute. So whereas on the left-hand side of this slide here, you see there's 3 tasks on one instance. On the right-hand side, there's 3 tasks on 3 instances. And what that means is we have to download the data every single time for each task. And corresponding, relating this back a little bit, if you're running a web server on AWS Fargate and you scale from 2 tasks to 3 tasks, you have to download your container image for that 3rd task. And that can take some time, especially if the container image is in the hundreds of megabytes or even in the gigabytes. And so this is a real area that customers talk to us about, and they say, how can we reduce the time it takes for Fargate to scale? How can we be more reactive? And a lot of it is all around container images and all around movement of data. And it's as Maish mentioned, it's a different problem than you have necessarily on like the Lambda side, but it's kind of the problems are similar. How can we reduce our scale out time? How can we be more reactive? Yeah, so that's kind of the background of today's conversation, and we're trying to work out how customers can scale quicker. And I'm just kind of changing diagrams a little bit. You brought up another one, and one of the ways when we looked at this and we've been kind of constantly behind the scenes iterating on Fargate performance and making it quicker to scale out. But one of the things that we realized has the biggest impact is that container image. It's not provisioning the instance. It's not attaching the network interface. It is downloading that data. And because there's that layer of variability, we don't know if we're going to be downloading a machine learning container image, or we're downloading a web server container image, or we're downloading a Python pandas data processing container image. That level of variability prevents us from caching as much data as we'd like to. Yeah, so that's kind of some of the background on what we're talking about today, and how customers can improve their Fargate task sizes with different technologies to optimize container images. And like,
before you continue, there was actually a question. Thank you, Norman, for chiming in, and I'm going to pop this up. So firstly, are these upcoming optimizations revolved around only ECS or also ECR? So firstly, if I remember correctly, these are not upcoming optimizations. These are already available for you today in production for your account. And I'll let you answer the second part of where this is available on what part of ECS and how.
Yeah, absolutely. So yeah, it's a good question, and I think I'm going to talking more broadly. There's lots of container image best practices that you can do that would be applicable regardless of where you run your containers. I mean, things like reducing the size of your container image by removing unnecessary libraries and binaries, and techniques like that are applicable everywhere. This in particular, we're going to start talking about some technologies that actually lazy load container image data, and we'll dive into what I actually mean by that. But the lazy loading technology we talk about today are all based around open standards. They can be ran inside of Fargate, outside of Fargate, using ECR, using other container registries. There isn't any optimizations that we'll talk about today that are necessarily specific to ECS and ECR. I would just say that that caveat of like scaling out multiple replicas being quite slow is more of a Fargate problem because of that single tenant, one task per instance. So it's less of a problem per se, or there's more solutions available to you on an ECS EC2 or a just EC2 or any other environment.
So you mentioned lazy loading. When I hear that, I kind of think for a person who's not really, when I'm not really happy to load the dishwasher at home and I'm really, really tired at the end of the day. So that's my kind of lazy loading. But I assume you're talking about something else about this, because there is, of course, I would say, not a scientific, but there's the speed of light which we have to adhere. There's certain things we can move faster than the speed of light. And the fact is, networking, pulling bits and bytes over the network takes time, and we can go faster than the speed of light. But we kind of didn't go faster, but with using this, what we call lazy loading, or what you're going to introduce in a minute, SOCI, is it kind of alleviates the problem and helps us get around this issue, or at least makes it a lot faster than we usually do. Well, I have been doing up until now.
Yeah, absolutely. And I want to kind of introduce lazy loading first, but by referring to an academic study that was done a little bit of time ago. It was actually done in 2016, but it was super interesting. And Harter and a group of academics did some research around data that people package up inside of container images. And one of the things that they found, or one of the outcomes they found, is that in the time it takes to start a container, 76% of that time is all around moving data, whether that's downloading it from registries, extracting the compressed tables into file systems. And so a lot of time is spent up front, but all of the data that is being moved around, only 6.4% of it is actually required to do useful work. So kind of setting the scene a little bit, you're downloading lots of container image data. You're downloading full container images with like lots of binaries and libraries and things like that. But Harter and his team found that barely any of that data is actually used for the application to work inside of the container image. And this was kind of like a super interesting study, and there's kind of off the back of it, there's been lots of work around like how can we use this in the technologies that we run. And we took actually inspiration from web developers, and this idea of lazy loading is quite familiar in the web development world. And it's this idea of, instead of downloading a full website up front, you download parts of the websites when users browse to it, or scroll down pages, or interact with specific parts. And we said, well, can the same apply to a container image? Instead of us downloading a full container image up front and downloading the gigabyte of data that someone has pushed to ECR, can we instead kind of reverse engineer and do some lazy loading and say, well, we're not going to download anything until somebody tries to access that file. And then when somebody tries to access that file, like the application tries to start up or something like that, we'll go and lazy load it. And by doing so, in theory, you back to the Harter study, you're only downloading 6% of the container image, because you're not downloading any of the data that you don't need to do useful work at the beginning. And this is kind of led us on a multi-year journey to explore lazy loading and seeing how it can relate to the various AWS container services, and how it can fit into the container world more broadly. Because we're not the only one looking at this. There's been lots of awesome interesting open source projects in the community around lazy loading container images, and they all kind of approach this problem slightly differently, but they're all kind of coming at it from the same place of, I don't want to wait for my image to be downloaded. I want to start almost instantaneously and get data as and when.
So I have questions for you, but before I get to your question, there was a comment from 27 Blends about the question of the speed of light. What I was talking about the speed of light is to move a gigabyte of or 10 gigabytes of data over the network takes X amount of time, no matter how. There's a limit to how fast we can make that go across the network. So what I'm saying is and that's because that's physics. There's nothing else you can do because that's the speed of light. Network and traffic and signals travel over networks at a certain speed. So we can make the network, in certain cases, we can do as much as we can by making it go faster, but there is a limit to how much we can do. And no matter how much we push, it won't be able to make things load faster in a certain way on that kind of. So in other words, we can't change the bandwidth or the pipe which is coming down from pulling the container from ECR or pulling it from a storage mechanism or a Docker repository somewhere else on the internet. There are certain limitations, so we decided to tackle that a different way. Going back to my questions. So you said, I love your analogy of the fact, okay, we have a website, and only when I scroll down to it or scroll down to that part of the page, then that piece of the page will actually load. So we don't have to load everything in the background and wait for everything. So how is it done with containers? I mean, how do you know which parts of the container you are going to be loading up in the beginning and which parts can be pulled as they're accessed? How does it actually work?
Yeah, there's lots of different ways to solve that problem, and I guess I'll talk about it today through the implementation that we use in Fargate.
Okay.
And the implementation that we use in Fargate is something called Seekable OCI, or SOCI for short. And this is a completely open source project. This is some technology that we originally open sourced back in 2022, and then have constantly been working on it and introducing it into some of our managed services. But the way that SOCI solves that problem is two steps. So the first thing that you need to be able to do to lazy load a container image is you need to be able to, I guess, identify what data is stored inside of that image. Traditionally, a registry doesn't know or care what it's storing. It's just storing a big compressed blob. It has no knowledge. It doesn't have a table of contents or any description. So the first way that we need to solve this problem is we need to be able to I guess inventory out our container images. And so we need a list of all the files that are stored in there, and we also need reference to where those files are in the big compressed blob. And for those unaware, that container images, when stored in a registry, they are normally a compressed, a tar-gzipped tarball. And so, if I want to go and grab a particular file, the previous method was download the full tarball to my server, extract the gzip tarball to its raw state, and then start walking through the file system. And so one of the ways that we solve this with SOCI is we create what we call is a SOCI index. And a SOCI index, as you might be able to see from the right-hand side, if not, I'll find the bigger diagram. The first thing it does is it lists all of the files that are stored in the container image and which compressed tarball they are stored in. And so here you can see a list of files and their offset to where they are stored inside of the tarball. And we kind of write all this out, and the kind of next step we do is we then carve up the compressed tarball into what we call as spans. These are like logical chunks. So, if you imagine you had a 1 gigabyte compressed tarball, we would pick a span size, I don't know, let's say 50 meg, and then you would have X many, 20 spans, all of 50 meg. And within each span, we know, back to the previous slide, there are these files. And so we now have a way of almost inventorying out our container image. We know what files are stored, we know where in the registry they are, and we can then go and get them. So that solves one part of the problem. We've now got I guess a map to the files. The second part, to answer your question, is that we've implemented, or when you use Seekable OCI, your container images are running on a Fuse file system. And Fuse, if you weren't aware, is file system and user space. It's a way to I guess an alternative, instead of running a different place to run the file system. And what we're able to do with Fuse is we're able to basically catch when the application attempts to access a file we don't have locally. And if it attempts to access a file we don't have locally, we intercept that, and we go speak to the registry, look inside of our table of contents, find the file, download the span, and we're good to go. And once it's been downloaded once, it doesn't have to be downloaded again. You can access that file lots and lots of times now because it's just locally on the file system. So you only kind of have that penalty to go and fetch it once. But yeah, that's kind of how we're able to do it. It's sort of intercepting at the file system level, and then we have this inventory in the registry to go and query.
So let me see if I can take a practical example. If we take whatever, for example, on the screen. So
Yep.
say I am running as you can see from what this looks like, an Ubuntu kind of image. I start my container up, and I know that when I start my container up, I'm going to be accessing the etc group, the passwd, and the bin bash commands. And they're all located in one of those spans.
Yep.
So when I try to access that, then we will intercept that in the background, already pull that image for you, or that span, in this case, whatever part of that image.
Yep.
And make it available. And
Yes.
say, for example, the second command in my container is to run apt-get update, which is in a different span, and I haven't used it before, so I haven't pulled that before. So in other words, and say, for example, the apt-get update for some reason was 3 gigabytes in size, which it never is, but still, just for the sake of the argument. But before, in other words, if I would have to wait up until now, I would have pulled everything at the same time, waited for those 3 gigs to come down, and would have taken time. But now, since the first 2 operations that I used was using passwd, etc group, and bin bash, those commands could complete before on that small span. And only when I access the piece of that app, then we'll pull that big chunk down, allow me to use that extra piece of the command. And that's what we call it. That's how we only load exactly what you're needing pretty much at that time. And only when you need it, we'll bring that specific piece down. Is that correct?
Yeah, absolutely. And then you can see, I guess, kind of relating this all back, that how this is a slightly different mechanism to how container images normally work. Where a container image normally works is we download everything, regardless if it's going to be accessed or not. We download it all up front, and this can be tens of seconds, if not even minutes. And so back to the original problem statement of, hey, I need to scale out quickly, and on Fargate I'm going to have to download a container image every time I scale. Well, if downloading a container image every time I scale takes 2 minutes or 1 minute or 30 seconds, like that is time where nothing else is happening in the infrastructure apart from data being moved from a registry to a server. And with lazy loading, we can say, well, let's not move the data yet, and let's wait and see what the application wants. And then when the application wants it, we'll go and get it from the registry.
But I want to ask one question, which I think we have to also clarify, is the fact that it is not as if we actually wait until eternity, until somebody actually wants to access that last pass or that last piece of the container image. Is that correct? In other words, for example, if all I did was use those 3 commands, bash, passwd, and group, and the last command that I run was user bin apt. Assuming that I had 40 different commands before that, which could have taken a minute and a half before. We don't wait until eternity until to get the last part of the image until you actually request it. We'll start loading it in the background for you to bring it down. So it will already be there before you actually ask for it. But we will always load the things which you need now first, and things which haven't been asked for, we'll start pulling in the background in order to make them available for you when you actually do need them.
Yeah, absolutely. So see lazy loading as technology to improve startup rather than technology that's going to reduce the amount of data transfer. Because as Maish mentioned, after the container has started, I believe it's after 30 seconds of the container has been running, we will start behind the scenes downloading all of the spans anyway, just in case. But in that first 30 seconds, we will only grab the data that your application needs to start. And as we've learned through the Harter study, it's actually only 6% of your data. So there's a real benefit that you get on startup through lazy loading and through technologies like Seekable OCI. But then behind the scenes, we'll absolutely be background fetching your data so that a few minutes in, if you try and access a file, there is no latency penalty while we go and get it from the registry. It's already there.
Yep. Okay.
Awesome. So yeah, lots of I guess terminology. Hopefully, I've clarified everything. If there's any questions around some of the terms I've used, feel free to ask them in the comments. We'll pick them up and try and define them a little bit.
Okay.
Okay. So I guess a few other things I did want to mention about SOCI. It is an open source technology. There's the SOCI, and it's implemented as a containerd snapshot, which is containerd, for those unaware, is a popular container runtime. It's what you use to start and stop containers. It's underneath Docker, like it's part of the Docker engine, but it's the bit that starts and stops containers. And SOCI is basically a plugin or an extension of containerd. So therefore, wherever you have ran containers, you can plug in SOCI and you can lazy load them. So we're talking about them here in the context of Fargate, but in theory, you can use SOCI and lazy loading technologies anywhere. There's no changes to your application to take advantage of lazy loading. Like you don't have to write your application in a certain way, or you don't have to package up your container images in a certain way. The OCI or Open Container Initiative standards for packaging container images, it's fine. We can use that, and we can lazy load container images stored in that format. So you don't have to convert them to some proprietary SOCI container image. The open source stuff will work fine. The only, I guess, step that you have to do to use SOCI is you have to generate the index, and that's the one I guess step that you might have to change from how you've built or packaged up container images before. Now, how do you do that? Well, there's two ways, and we'll jump into a demo in a moment to actually see this in action. But the first way to generate the inventory of what's in your container image is you use the SOCI CLI, and that is a binary that you can have in your pipelines, you can have on your build servers, you can have on your workstation. And basically, once you've built a container image through the normal tools, Docker build, for example, or any other container builder, you then use the SOCI CLI to generate its index. And that's the inventory that I was referring to, of which files are stored where. And then what we do is we store the SOCI index in ECR, in the container registry, alongside the container image. And so inside of your registry, you'll have two artifacts. You'll have your container image and you'll have its inventory. And that's the only steps that you need to do to take advantage of SOCI.
And Norman asked us a question, for example, for ECS, and we're talking about a task definition is like the configuration of what I'm going to run in my container on ECS and Fargate. And there is no difference at all. In other words, it's completely transparent. You don't have to make any configuration or any flags or any specific definitions in your task definition to say this is a SOCI image. If it is one, it will pull it down that way, and the index is there. It will do lazy loading on Fargate. If it's not, then it won't. But you don't have to make any changes in your task definitions on ECS.
Yep, that's absolutely correct. Yep, there's no changes required. It's something that, because it's being done at the lower levels of like the containerd levels, we will inspect to see if that index exists, and if it's not, we will just download all the data up front. So yeah, your task definitions don't have to change. All you have to do is generate the index.
Are you ready to show us how this works?
Yeah. Behind the scenes prepping an environment. We'll see how this
if
goes.
It's ready or not.
Yeah. I'll just stop sharing that screen, and then I'm going to switch a little bit, switch some stuff around. All right. So let's open up the right session and make sure that everything is being set up. Okay. So, all right. Let me share this screen.
And of course, if you have any questions in the chat, anything you would like to ask, please do. We're here to answer. I know this is kind of a different show than usual, but we aim to please, and we try to help out, and also kind of shake things up every now and again as well to make things interesting for everybody else. And thank you, everybody, for joining and staying with us on the show. And back over to you, Olly.
Yeah, thank you. Yeah, so this is an AWS environment. I'm using Cloud9, which is a remote IDE as my workstation. And I'm going to show a demo just to compare like with SOCI and without SOCI, so with lazy loading and without. And I'm actually going to use a bit of a trendy demo application, and that's going to be a PyTorch machine learning serving application. And the reason why I'm going to use that in my demonstration is because some of the machine learning container images are some of the largest ones that we see.
Besides the Windows images.
Besides the Windows images, of course.
Windows images.
Of course, yeah. So I've already gone ahead and I've pushed my images to ECR. So what I've done is I've pushed a PyTorch image to ECR, and you can see that exists there as the latest tag. And I've pushed a second artifact called the SOCI index. And if you were kind of curious to see how that's created, that's created with the SOCI CLI. Maybe I'll back up a little bit actually and create a SOCI index in a moment. But I also have inside of ECR, I have a second PyTorch repository that just has the container image. It has no inventory. And so previously, in relation to one of the questions that came in, they said, how do I use lazy loading on ECS? How do I use lazy loading on Fargate? And the answer is you generate the inventory and we'll detect it from there. And so I have two repositories because I want to show the auto detection in action. Okay, so that's kind of what I have behind this, have pre-existing. So the next step I'm going to do to actually use these container images is I'm going to create some task definitions. And I'm unfortunately copying and pasting from a cheat sheet. So I'm just going to copy and paste it, and then I'll expand what I've just created. Is I've actually created two task definitions. One called PyTorch lazy and one called PyTorch no index. And this is a task definition. So as Maish mentioned, this is how we define our workloads on ECS. This is the file that we use, the workload declaration file. And it's reasonably self-explanatory. So we have a name for our task definition. We have some IAM permissions that we want to pass to our task definition, and we have the size of the task, how much CPU and memory we want it to run. Then within the task, we define containers. And I've defined 2 containers here. I've defined one container called Am I Lazy, which I'll explain what it is in a moment. And I have a second container, which is PyTorch, which is coming from my ECR repository.
Okay.
In that second task definition I created, it is absolutely identical, but the only difference is that I'm referring to that second image, the one that doesn't have an index, because I want to compare that they're going to be laser loaded or not. And like just for like full transparency, if you diff the 2 task definitions, you can see the only thing is the name is different and the image is different. Everything else is the same. So there's no special flags here. Now, to actually start those on ECS, we're going to create some ECS services. And so I'm just going to do that now. And once again, I'm just copying and pasting from my cheat sheet, and I'll expand what I had done. Okay, so now we have 2 more files. And this is a service definition. So this is me saying I would like to use my task definition, and I want it to be a long-running service. And I would like you to run 1 copy of my task definition, and if it fails, restart it. Like, this is my intent. This is my desired count. Passed in some networking configurations, so subnet security groups, and that's it really. This bottom bit here is built-in service discovery, and that means we can query our tasks using a host name. But we'll come to that in a moment. So run my services, the create service command. I didn't actually register my tasks. Let me do that. The joy of copying and pasting from my cheat sheet is when I scroll down too fast and miss some commands. All right. So now on my ECS cluster, I should have 2 services. And then behind the scenes, I should have, in a moment, 2 tasks being provisioned to correspond to my services. And remember that the whole point of this session is to talk about how we can start that task quicker, how we can go from nothing, which is what I had a minute ago, to running. And we're going to be doing that by lazy loading the top task and not lazy loading the bottom task. And we're going to kind of compare and contrast. Well, this one's activating already, so you can see here that the lazy loading one has started really quickly. We've not downloaded that full container image, and if you actually look, the container image is 1.2 gigabytes compressed. So uncompressed, it's going to be more than that. It's going to be probably more than 2 gigabytes, but compressed, it's that. And so the bottom task is going to take a little bit of time because it's having to download all of that data and then extract it. But the first task started almost instantly. And we can actually even just query the PyTorch serving container now to see if it's actually running. This is a DNS name for my task, which is the service discovery, and I've hit ping, and you can see now that that task is pretty healthy. Whereas if I ping the other one, it's still not running. It's still not ready yet because we're downloading all that image up front. While we wait for that one to start, we may as well poke at the one that was laser loaded to make sure that it's all working correctly. So let me see if I can see if I have any models available. I do, yep. So I'm serving the DenseNet model, which, of those who are unfamiliar, it's a popular image recognition model. And I should actually even be able to test it. And so I have a picture of a flower stored in an S3 bucket. And if I download the picture of the flower, which, just a picture of a flower, if I send that to PyTorch, it should hopefully recognize that it's a flower. So sending it, and there we go. Recognized it's a flower. So like the app doesn't make too much difference, but what we were able to do is lazy load it very, very quickly, get only the bits we need to start our model and to start serving it. And hopefully, there we go. We finally got that second task running. And if I go back to the original ping, yeah, there we go. The original one is now active. Now, just to kind of put some like data points behind this, a lot of people kind of say, well, this, all right, you've started 2 tasks. Like how impactful is SOCI? Well, inside of ECS, every time a task starts or stops, it generates an event. And I've captured those events and I've sent them to a CloudWatch log group. And what we can do is we can query that log group and kind of play around with those events. So inside of my IDE here, I actually have a log query Python script that is going to talk to CloudWatch logs. It's going to grab the events from the tasks, so when they went from provisioning to running to stopping, and just compare some timestamps. And so just looking at the raw events that would have just started a couple of minutes ago, you can see that the one that was non-lazy loaded took 103 seconds to start. So, just shy of 2 minutes. Whereas you can see the one that was lazy loaded went from nothing to running in 30 seconds. And that's close to like a 70% improvement for this particular use case. And obviously it will vary a lot depending on the container images and the access patterns of the application at startup time. But in my PyTorch example, and this was a like stock PyTorch container image. I haven't done anything to it to optimize it in any way, shape, or form. You can see that I have a noticeable startup improvement. And remember, like this, if you were a web server and you're scaling out to meet traffic, this is a great use case. Or if you're an event-driven architecture that's part of a synchronous flow, and obviously the bigger the container image also will have an impact on the performance difference. I will caveat that and say this won't work too well for smaller container images. So if you have like containerized microservices, like a Golang or Rust microservice that's like 10 meg, it's quick enough to download that data. There's no need to lazy load it. But if you kind of the tipping point we've come to is around about 250 meg. If your container image is larger than 250 meg, it's worth investigating SOCI to reduce its launch time.
So we're coming up until 12 minutes till the end of the show. There were a couple of questions which came in, and there's something which I think you still owe us. We'll get to that in a second. The first thing is, the question was, does lazy loading work for Fargate on EKS or only ECS?
So at this time, it only works on ECS and Fargate. It does not work on EKS on Fargate. It can work on EC2s. It's just a containerd plugin, so you can install the plugin on, or it's a containerd snapshot to use the official term. So you can use it anywhere you use containerd. It's not available yet on EKS Fargate. That's something we're working with the EKS team to enable, but it is there on ECS Fargate, and it is something that you can enable on any box you have control.
Perfect. Thank you very much, Patrick, for that question. And the most important second big question is, I've known you for quite a while, but I still don't have the answers. How do you copy and paste so fast?
How do I copy and paste so fast? Well,
Yep.
If you want to see behind the curtain, we've built a workshop for SOCI, and this is a workshop that you can run at AWS events like reInvent, or you can get your account team to run. And so behind the scenes, I have the instructions for the workshop, and they have a nice little copy button. Is
Awesome.
how I'm able to copy and paste so quickly.
So it's not rocket science. You're kind of cheating, but it's okay. But we're getting everybody the same the same cheat sheets as well, so they can do it themselves.
Absolutely, yes, yeah, and when we get towards the end and we want to talk about call to actions, if you want to learn more about SOCI, obviously everything's open source, the documentation's open source. But yes, if you're coming to an AWS event or you want to reach out to your account teams to run the workshop, you can even get those instructions that I'm copying and pasting from behind the scenes.
The one last part that you said you were going to show us is how do you actually create that SOCI index, which we didn't see on the Docker image. Can someone even show us?
Yeah, I can do that, absolutely. So I'm going to do some more quick copying and pasting actually. So right now on my server, I don't think I have any container images, and I need a container image locally to be able to generate that index. So I'm just going to create a container image, and just to show what I've copy and pasted to see what's behind here, I've created a Docker file, and a Docker file is how you define what's in a container image. And I've created a static HTML web page.
Okay.
So I can turn that bit of content into a container image with a build command. So this is using nerdctl or nerdctl build, but Docker build is an alternative, which will do exactly the same thing. And this is me just creating a container image on the server. Once this is done, it should take a couple of seconds to generate. It's only an Nginx web server with one page.
You're doing a Yum update, so it takes a while.
It does. We can then absolutely index it. So that should finish with that. You can just download a container image from a registry. You don't have to build it to index it. I could have just done a pull of the Nginx image. That might have actually been quicker in this context. But I guess showing full transparency, there's nothing I'm doing in Docker files here to be useful for SOCI. That's one of the things we wanted to do with design decisions, is we didn't want to make people change the way that they build their container image. So just doing an image list, I now have my Nginx demo. It's local. It's 650 meg, which is very large for an Nginx web server. And I then just use the SOCI CLI to index it. And so the SOCI CLI is a binary I have locally on my machine. And then if I just did SOCI create Nginx, and that didn't go very well. I'm not sure why not. This is what happens when I go off my cheat sheet.
Okay, I'm sorry for doing that.
No, it's all good. I know why. It probably wants the full reserved full name, including registry. So let me rename it. So it's so I now have a full ECR URI. I could have done it with the Nginx one, but it would have been a different URI. I can now do SOCI create of this full image name. And so what we're doing now is we're inventorying, and we inventory a layer at a time. So my image has actually only got 3 layers. And so what I have done is I've inventoried every single layer. The top layer was skipped, and it was skipped because it was a really small layer. It was less than 10 megabytes. And we decided that there's no benefit in lazy loading something that small. We'll just download that 10 megabytes as it is. But the bottom 2 are quite large layers, and those are the ones that we're going to want to lazy load. So those are the ones that we'll create the index for. And if you were curious to see what it looks like, if I do the what should I do? Actually, you can. What I've done here is I've just done a SOCI index info, which is a way to expand, and I've passed in the digest. And you can now see what the index looks like. And for those that have poked at container images before, this is an OCI image manifest. This is a manifest file that defines lots of things, but is more commonly used to define a container image. It's what we've used to package up the SOCI index. So you can see that the media type is SOCI index, but the actual manifest is OCI, which means I can push and store this in a registry alongside container images. Cool. Is there any other questions or any other things I owe you, Maish? I don't want to.
I think not. I think we're going to kind of stop here because I want to leave a few things for leaving a bit of householding for the serverless land office hours. And let me just share my screen and take over your screen share if you don't mind.
Yep.
So the first things first are these are our details. If you want to get hold of us, ask more questions, look us up on LinkedIn. You can ping me on Twitter or X, whatever you want to call it. I'm always going to call it Twitter. It's fine. So give us a ping if you have any questions. We'll be happy to give you to interact and to comment and to speak with you guys and give you some more information or links. Do you have by any chance that workshop that you want to do? Is that workshop available for everybody to use, or is it only through a specific account with an AWS account?
No. The documentation is public. You can read through the documentation that is available. You won't have, if you do it at an AWS event, it will be like a pre-existing. It will be a pre-existing account with the images loaded, but you can absolutely follow along to the documentation outside. I've just pasted you the link there, Maish.
Okay. So let me just quickly put it up. Where am I? Yeah. So this is the actual workshop that you can. Actually, I'm going to paste it here in the comments. And is there a link for SOCI documentation for also somebody asked?
Yeah, absolutely. So everything from the SOCI open source repository has all of the documentation, has all the source code, has the CLI binary that I just used. And then there is specific documentation as well on how to use it with Fargate. And so I can send you the ECS documentation as well. But the SOCI GitHub repo is the best place for all of it.
Perfect. So we are going to be coming to the end of the stream. And before we do, I want to firstly thank Julian for giving us the opportunity to come and speak or blab about whatever you want to talk. I understand it was very interesting. So thank you very much for the comments from the chat. I was glad it was interesting. Next stream is going to be in a week's time, same place. We're going to have another guest host, Giuseppe Battista, which will be talking about cost-effective Gen AI. Don't forget, you can subscribe through the Twitch channel, Serverless on YouTube, or through the LinkedIn channel. And the last thing that I wanted to see over here was, don't forget, of course, all the content which is available for our customers. And I'll build this here on serverless, on Lambda, is available at serverlessland.com. This show, of course, will be also available after we finish the broadcast. You can also consume it there on demand. Any closing comments before we shut down for the day?
No, I don't think so. I say, thank you for giving me the opportunity. It's always funny to see when the container and the serverless teams cross over, and it's really nice to present to a new audience. So thank you for having me.
Yep. And I'll second that again. Thank you very much. Thank you, everybody, for being a wonderful audience. Thank you for the interaction, and hopefully we will see you sometime in the future. Have a good day.